Hi everyone, welcome to another video by Cheenta. I am Rajdeep, and in today's video, we continue our discussion of irreducibility from the previous video. Last time, we saw the basic definition of irreducibility and Gauss's lemma. We used that to prove the irrationality of square root of t with a much simpler method than the standard one. If you haven't watched it, I would urge you to go and watch it. Sorry. Because we need the tools and the ideas from last time. For today's video, where I'll discuss Eisenstein's criteria. We'll use that to prove two problems, one of which is the irreducibility of cyclotomic polynomials, a fact that I brought up and just showed you in my last video on irreducibility, and also a problem from the IMO 1993. I hope you enjoyed, and let's get into it.
Right. So here's a picture of Eisenstein. He was not just known for Eisenstein's criterion, which is a much more basic result. He was a pioneer, a great mathematician in his own right, leading to many developments in number theory and analysis. Great mathematician. This is the problem from the IMO 1993. It's the first problem of the year. Let f of x is equal to x to the power n plus 5x to the n minus 1 plus 3, where n greater than 1 is an integer. And essentially, what follows is the definition of irreducibility. We want to show that f of x here is irreducible. Right? We'll not get directly into it, but feel free to pause the video and try the problem on your own. There's many things you can try, but it's still a hard problem. Before we get into this, I will talk about the main result of today's class, which is Eisenstein's criterion. Let's see what it says. It says that given a polynomial, an integer polynomial, f of x is equal to a0, rather, let's start the other way, an x to the power n, an minus 1 x to the power n minus 1, all the way up to a1x plus a0. Integer polynomial, which means all the ai are integers. Right? Start with the polynomial like this. Then, if it so happens that there is a prime, say, rather if there is a prime p such that p divides every single coefficient of f except the leading coefficient, ai, for all I between 0 and n minus 1. So starting from this coefficient all the way up to the constant. If p divides all of them such that p divides ai, and p squared does not divide the constant term, right? P divides all of them, but p squared does not divide a0, then f of x is irreducible, or irreducible over z, and hence by Gauss's lemma over q as well. This is the result. So take some time to get comfortable with it. It's kind of surprising because in some way this is an extrinsic result, at least it looks like one. We don't use anything intrinsic about f of x, at least directly. Of course, the coefficients will be involved, but it's like some extra prime is coming from outside and doing something about the polynomial or giving us some information, like a shadow of the information of the polynomial, and that's enough to give us irreducibility. The proof is very nice, and I will give the proof for this because it will be very helpful for us. It's a very potent idea as well. Even when we don't have z and we have other sets, as I said, rings in the last video, the idea that goes into the proof of Eisenstein is very helpful. And the idea is going modulo p. So the basic framework that goes into these kinds of things is that if you have some f of x which is reducible, it splits as some non-constant polynomials px into qx, then if you reduce the entire equation modulo p, right, and all of these are integer polynomials, so all the coefficients involved are integer, What do I mean by going modulo p or reducing a polynomial modulo p? Just reduce all the coefficients modulo p and sort of work within the framework of modulo p. So if you just look at the polynomial modulo p, which means all the coefficients are being worked modulo p, and all the roots will be worked modulo p. So which just means reduce all coefficients mod p. And so if I do that, I write the reduced version of f of x as f bar x, which just means all the coefficients are reduced mod p. Right? Since these are equal things, they will stay equal when I go modulo p. So in particular, unless something very uncanny happens, which is this guy having a leading coefficient being divisible by p, but we never have that kind of an issue because we usually deal with monic polynomials. As in the leading coefficient is 1, so you never really get that kind of an issue. So unless something like that happens, in which case you actually are in trouble because the degree of the polynomial actually goes down. You're no longer working with. So my point that I'm trying to make is if you had, pxn, rather, let's take a proper example, 3x squared plus 2x plus 1. If I look at this polynomial mod 3, the leading coefficient actually dies. So this becomes 0 mod 3, right? If I look at this thing, rather make it 4 to drive my point home. 3x squared plus 2x plus 4. If I reduce this mod 3, this actually becomes 2x plus 1. And suddenly I'm dealing with very different kinds of polynomials. Like we've lost essential data here, which is the degree. So unless this kind of a degeneracy happens, you're still retaining some good amount of the data. So as long as this does not happen, we have retained data. And if f of x is equal to px into qx, if fx is reducible over z, it must be reducible modulo p for any p, right? In some ways, reducibility is a big statement. It's a big shout over the large global domain of z. So if something big is happening globally, that big thing will happen locally. So if reducibility happens globally, reducibility will happen locally, which is modulo anything. The converse is not. So you can have splits modulo specific numbers, but that doesn't imply having a split in z. A simple example of this is x squared minus 2 mod 7 or something like that, I think. The point is that you do get, I think, mod 7. Mod 7, since if I plug in 3 here, right, 3 squared minus 2 is 9, which is 0, right, mod 7. Sorry, 3 squared is 9 minus 2 is 7 mod 7, which is 0 mod 7, which implies that 3 is a root, which implies minus 3 is a root. Also, this is like I'm slipping it in as a technicality, but this is an important result, which happens because you're working modulo primes. This kind of thing does happen when you're working modulo primes. I will not get into why, but all the intuition that you have from working over the integers, factor theorem, remainder theorem. So I will just slip this in as a technicality so that you don't have to worry about these things. Factor theorem, remainder theorem, polynomial factorization. Everything works the same way. An n degree polynomial has at most n roots. If alpha is a root, then x minus alpha is a factor of the polynomial. All of that works even when you're going mod p. Polynomial factorization works mod p. So I'm slipping this in as a technicality, but this is by no means trivial, something that needs to be proven. But yeah, it does work. And so that tells me that x squared minus 2 actually does factorize mod 7, right? It factorizes as x minus 3 times x plus 3, right? Mod 7. And you can also see this, x minus 3 times x plus 3, no matter where you are, is x squared minus 9. But x squared minus 9 is the same thing as x squared minus 2. So you do get a factorization mod 7, but you don't get one over the actual global domain. But this gives you a cool trick. If something is reducible, in Z, it must be reducible mod P for any P. which means that if a certain polynomial is shown to be irreducible, right? Not reducible, mod p for any p, it must mean that it was irreducible over integers as well. This is like a simple logical leap that I've made here. Irreducible modulo any prime implies irreducible at the top, which is over the integers, because if it was reducible here, it would be reducible mod p as well. That's a cool trick. So, all that being said, if I look at the condition of Eisenstein, I have this polynomial, like integer polynomial, and I have a special prime p for which something interesting happens. So I'll go modulo that prime. Look at f of x mod p. For the sake of contradiction, let's assume f is reducible. Let's assume, which implies I can write it as a product of non-constant polynomials over the integers. So say it's reducible over z, right? That's the actual contradiction to our original claim. We claimed that it was irreducible, so say it's reducible for the sake of contradiction. F of x is equal to px into qx. Now I reduce this equation modulo p. F bar x is p bar x times q bar x, right? But something very interesting that happens is that since f bar x, since in fx all of these coefficients are divisible, by p, all of them become 0 when you go mod p, right? So it's like if I had the polynomial x cubed plus 3x squared plus 6x plus 9, if I looked at it mod p, this would just become x cubed mod 3.
What class are you? Why should we put it?
Video jokes. Right? So it's the same thing that happens. Since every coefficient except the leading coefficient of f is divisible by p, when you go mod p, they all become 0. So f bar x is actually the polynomial an xn. Well, an bar. We just reduced that mod p. Which implies what? It implies that both p bar x and q bar x must also be of this form, right? X to the n can only ever be factorized as some x to the r times some x to the s. Right? So what does that mean? That whatever px and qx were, when you reduce them mod p, they look like this. Which means every coefficient except leading, as in the coefficient of the highest degree term, every coefficient of both px and qx, except the leading coefficients, are divisible by p. Right? If px and qx originally were some polynomials, some say b0 plus b1x plus blah blah br x to the power r, and this is the same thing. Since after reducing they look like this, all of the other coefficients must be divisible by p. But here's the trick: both of their constant terms are divisible by p, which implies if the constant term of px is say b0 and the constant term of qx is c0, p divides both of them, right? Since the constant term dies for both of them mod p, as I just said. But if p divides b0 and p divides c0, that means p square divides b0 c0, the product. But b0 c0 is the constant term of f of x, right? Px into qx is f of x, so the constant terms multiply. The constant term of f of x, a0, is the product of b0 and c0, but that's divisible by p square in this setup, which contradicts our original assumption that p square didn't divide a0. That's where the contradiction is. So I urge you to sort of go back to the proof from the start and see where the real thing that happened, what actually gives us what's the content of the proof. But yeah, that's the contradiction. Hence, fx must be irreducible over z. So, as I said, so this is a non-example of something that can be solved by Eisenstein, since even though all the non-leading coefficients are divisible by 3. Unfortunately, the constant term is also divisible by 9. So Eisenstein doesn't help us here. So this is a non-example, unfortunately. What is an example? Something like this. X squared plus 3x plus 6x plus 12. One shot, this Eisenstein tells me that this is irreducible because 3 divides every non-leading coefficient and 9 does not divide the constant. That's very powerful. As I said, as I promised, there's 2 applications. Application 1. Application 1 is cyclotomic polynomials. What are they? They're these polynomials. X to the p minus 1 plus x to the p minus 2 all the way up to 1, where p is a prime. As it turns out, these are irreducible. Clearly, Eisenstein doesn't help us here, right? Because of obvious reasons, there's just no primes that divide the coefficients. So what do? This is where a standard trick comes into play. It's called shifting. So instead of working with px, I'll show that p of x plus 1 is reducible. But if p of x plus 1 is reducible, that actually does imply that px is also reducible. Why? Because if px could be written, by contradiction, if px could be written as qx into rx, px plus 1 would be qx plus 1 times rx plus 1. So if this is irreducible, so must this be. But now we have a much better polynomial. P of x plus 1 is x plus 1 to the power p minus 1 plus x plus 1 to the power p minus 2 all the way up to 1. What is the constant term? It's 1 plus 1 all the way up to 1, right? So it's divisible by p. You could do this. You could collapse all of the, you could not collapse, but individually compute the coefficients and do the whole thing. But we can do something much cleverer here, which is notice that this is a GP, right? This is just x plus 1 to the power p minus 1 by x plus 1 minus 1, right? It's a finite GP with common quotient, if you will, x plus 1, which is just x plus 1 to the power p minus 1 by x. Right, which is just, what is this? This is x to the p plus, p choose 1, x to the p minus 1 plus p choose 2, x to the p minus 2, all the way up to 1. But there's a minus 1, so that dies. This is just p choose p minus 1, x divided by x. So this is just nice. X to the p minus 1 plus p choose 1, x to the p minus 2, all the way up to p choose p minus 1. But this is where I'll use a result that is very well known in Olympiad circles. It's a well-known result in general. I will not prove it here. That's homework for you. It's an interesting problem in its own right. That p divides p choose I for any I between 0 and between 1 and p minus 1. Sorry, I'm right. Obviously, p choose 0 and p choose p are 1, so obviously p doesn't divide that. But every other one it does, right? P choose 1 is p. P obviously divides that. P choose 2 is p into p minus 1 by 2. That's divisible by p because p minus 1 by 2 is an integer on account of p being odd, as it's a prime. I should probably mention that p is a prime greater than 2. In the case of p equal to 2, it's obviously irreducible because it's a linear polynomial. It's just x plus 1. Yeah. So since this is the case, p divides all of these coefficients. The last coefficient is just p. So it's x to the p minus 1 plus p into something times x to the p minus 2, blah, blah, blah. Finally, a p. P squared doesn't divide p, right? Obviously. Hence, this is Eisenstein at p. That's how we say that Eisenstein's theorem for the prime p applies. So it's Eisenstein at p, hence irreducible. It's a very nice application. Finally, the problem that I started with, this one. X to the n plus 5x to the power n minus 1 plus 3. Right. Obviously, here also Eisenstein doesn't immediately give us. And if you even tried shifting, that won't get you far either. So seems to be that Eisenstein doesn't help you at all. What are you going to do at that point? There is a solution using something known as Perron's criterion, which is a more exotic tool. It has to do with the sizes of the coefficients and so on. I'll not get into that. But it also is a very beautiful proof using the proof of Eisenstein in some way. The thing that had disprove Eisenstein, that is what helps us here. There's only two meaningful primes you can go for this guy, right? If you want to show that this is irreducible, you could show that it's irreducible modulo some, decent prime. You really only have two choices, 3 and 5. Because modulo any a larger prime, the polynomial stays intact. You don't actually get any reduction, no help as such. So you can either go mod 5 or mod 3. In this case, going mod 3 is the right thing. Mod 5 actually doesn't give you much again. If you go mod 3, the last term dies. So you just have x to the n plus 2x into n minus 1. You can keep it 5 if you want. It's kind of irrelevant. You might say, okay, so for the sake of contradiction, assume that it's reducible. For the sake of contradiction, assume that, sorry, my bad actually. It's obviously reducible, right? It's just x to the n minus 1 times x plus 2. My apologies. It's obviously reducible. So, do we stop? Is there any help that we can get? The thing is that I still have the same technique that I used. After I reduce, so I have f of x, which is my original polynomial. Say it was reducible for the sake of contradiction. Say. Then once I reduce it, this thing just becomes x to the n plus 2x n minus 1 after reduction, mod 3. And these guys become p bar x times q bar x. This is all assuming, for the sake of contradiction, that f is reducible. But this thing is x to the n minus 1 times x plus 2. X is irreducible, x plus 2 is irreducible. So it's kind of, as I've said multiple times before, there's a lot of equivalence in the algebra of polynomials and primes, and the integers, for example. So if I think of this, it's kind of like if I had two primes and I had p to the n minus 1 and q, and this was a product of two numbers a and b. All you could say is that this q sits inside one of these two guys, which one is concerned to us, and the rest is just p to the n minus 1 splitting somehow, which implies that without loss of generality, I can say that a is some p to the r times b without loss of generality, and b is p to the s, where r plus s is equal to n minus 1. Right? The p splits into some smaller powers, and q goes with one of the guys. The exact same thing happens here. These two are irreducible, which means that p bar x is some x to the power x plus 2 for some r less than or equal to n minus 1, and q bar x is some x to the power s, again without loss of generality, where r plus s is equal to n minus 1. This is the thing that I did here is really just like analogy. It's not math per se. That equality sign it's really just it's an analogy. It's one that is a good one, but it's end of the day just an analogy. So p bar x is that, and q bar x is this. So p bar x is x to the r times x plus 2. Q bar x is x to the s. Here's a cool trick. If s is greater than 2, something bad happens, which is if r is greater than equal to 1 even for that matter. Rather, the point is that as long as p bar x doesn't have a constant term, something bad happens, which is that this is x to the r plus 1 times 2 into x to the r. If r is not 0, then this implies that the constant term of both p and x in the original versions are divisible by 3, right? If r is greater than or equal to 1, so if r is greater than or equal to 1, say px was originally some polynomial of degree r plus 1, right? The degrees won't change. Some r plus 1 plus AR plus 1R plus 1, blah, 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 sub A0, such that after I reduce mod 3, that A0 vanished, which implies that 3 divides it, just like it happened in the Eisenstein proofs case. So 3 divides A0, right? The constant term of this, and obviously 3 divides the constant term of Qx. So yeah, if Qx was, again, some b to the bs, x to the s, all the way up to some b0, then 3 divides b0 as well. And you see where this is going. There is no 9 in the constant term of this. Since f of x is equal to px into qx, and the constant term of both of px and qx is divisible by 3, it must be that the constant term of s is divisible by 9, 3 into 3, which is not the case. So r must be equal to 0, which implies that the only way you can split f of x, if it were to be reducible, is if, p bar x was x plus 2, and q bar x was x to the n minus 1. That's the only possible split. So this is a subtle argument. Hopefully you caught it. But this implies that the original px was also a linear polynomial, right? Degrees don't change. And a linear polynomial, a linear factor, is the same thing as having a root. It's very easy to see that this guy does not have any integer roots, thanks to the rational root theorem. I will not, for the sake of brevity, I will not get into that. It's very easy to see that no integer roots exist for this. Hence, it must be irreducible. That is all for today. Hopefully you enjoyed the video. Thank you very much.